Okay, this afternoon we are talking again about polymers and try especially to see which are the techniques that allow making measurements on polymers. In particular, concentrating on thermal analysis, which is very critical on polymers since they have a temperature of a softening temperature and even a degradation temperature which is considerably low. So they may most of them they tend to soften at around 200 degrees or less, and they degrade just over 300 degrees or so. Then there is the glass transition temperature at which they become from glassy, they become rubbery, and this is a further transition to be calculated. So in practical terms, we have a number of possibilities to evaluate these chemical and physical processes. We have the differential scanning calorimetry and the differential thermal analysis, which are basically the comparison between the behavior, the thermal behavior of the polymer with the thermal behavior of something which is much more stable, therefore a metal, a very stable metal. Then we have the mass loss due to degradation, which is evaluated by thermogravimetry, and a number of different effects, in particular the viscoelastic. You may remember that polymers are always dependent on time. Their behavior is always dependent on time, so they have a kind of viscose and viscoelastic behavior, and in some cases it's even difficult to discern a completely elastic behavior. So there are a number of other considerations to do, for example, polarity and non-polarity in polymers. There are polymers which are definitely non-polar because they don't include any other elements than carbon and hydrogen. As a consequence, they have no particular polarity. The ones which are formed from hydrocarbons like polyethylene, polypropylene, polyethylene. And in other cases, they may have a small or larger polarity, which needs as well to be measured because it has consequences also on mechanical and thermal properties. Then there is the behavior during combustion, which is going to be treated a little bit next time. So the so-called evoluted gases analysis, the gas chromatography and mass spectrometry basically. So basically, you evaluate the gas development from polymers, and you see whether they are able to get to combustion or not, which is one important point. Also in the question of adding other anti-flammable additives, like it is often the case, to transform the polymer into a moldable and reproducible plastics. It's not just a question of avoiding fire, although it is an important objective, of course, but it's also a question to understand whether the polymer is sufficiently stable to be able to by a molding operation. Having said that, we had last time some discussion about glass transition temperature. So glass transition temperature may be in different intervals of temperature. And basically, if we want to have just clear-cut distinction, we can say that glass transition temperature might be higher than service temperature. Service temperature means that it's going to be around room temperature. So you can easily say, instead of service temperature, room temperature, you are about right. Most polymers are not used at temperature different, very different from room temperature. We can easily say that if service temperature is higher than glass transition temperature, that means that we use the polymers in a rubbery state. That means that they are elongable, considerably elongable, and they tend to be not rigid, not enough rigid, not enough stiff, if you want. And therefore, we have basically two categories and some polymers which are very effective to produce some glassy-like sheets. If you want sheets which are substitutive of glass, like it is the case for the last ones which we are showing in this graph, which are going to be polymethyl methacrylate, which in Europe is called plexiglass mainly, polystyrene and polycarbonate. Also cellulose acetate, but it's different. Its structure is different because it's very tends to be very polar. So in practical terms, it is not very suitable to make plates. But on the other side, it keeps this film, this transparent film structure appearance. The other ones are mainly used in the rubbery state. It is also interesting to find that, for example, polyvinyl acetate has a glass transition temperature which is worryingly close to room temperature, which means that in practice it is used only as a component in blends, in polymer blends. It is not only not not used in other as such, although it is a promising material. It's also very stretchable and resistant, but in other sense it's not used a lot because it tends to pass from glass to rubbery state, and which means that since you are doing the choice to use the polymer either for its elongation, so it's in the rubbery state, or for its stiffness, so in the glassy state, of change state during service, that means that your structure is going to be destroyed, which can happen, for example, with polypropylene. If you go under zero with polypropylene, you might have problems. In some cases, it's in order to get to lower temperature. Polypropylene is used a lot, for example, to make small containers, also for water and so on. And you may consider that needs to be additive in order to be able to get also to temperatures below zero, well below zero, also because it's used also for car bumpers combination with glass fibers, etc. So as the matrix for glass fiber composites. So how to determine in practice the glass transition temperature? There are some factors which influence them, the glass transition temperature. Of course, of time. So we might have cooling temp velocity, which influences a lot glass transition temperature. Also because we may have in this graph you see to the left, we have something which we call the cold crystallization. Cold crystallization means that since we have this already said that below we may have an interval. We have an interval of softening interval. So it passes from solid, a polymer passes from solid to fluid, and vice versa in an interval. Since it's not crystalline, it's mainly amorphous. So it doesn't have a precise crystallization temperature, which has also another consequence, that crystallization, although it doesn't involve the whole of the polymer, crystallization involves only part of the polymer because most of it remains amorphous. That means that you may have the influence of the velocity of cooling with respect of how the chains are arranged, so the length and order of molecular chains. And the other consequence is that crystallization occurs at different extent depending on which TC, so which temperature of cold crystallization. So crystallization below the solidification temperature, depending on how much you freeze, in a sense, you solidify the material below the solidification temperature. You have different extent of crystallization, and also you may have different extent to the interval of the melting interval, about the softening and interval. In other words, to be clearer, what is meant by this graph is that if we pass from crystallization, so we tend to make it solid, to solidify this material, and we go down to 15 degrees, we have a larger interval. If we go down just to 95 degrees, always with the same cooling velocity, we have a stricter, smaller interval, a small solidification interval. And this is important because molding, the material molding, polymer molding occurs above the high melting temperature. So we need to know where we are at the, above the high melting temperature. Of course, since the polymer degrades with temperature, and also because heating more costs more, of course, we tend to be as close as possible to the high melting temperature. We need to be higher than the high melting temperature, but not that much. But since this depends also on how we cool down, which temperature we cool down, that also controls the width of the interval, of the solidification interval. This is important also because when you cool down in the mold, when you have the injection molding of your polymer and you cool it down in the mold, once you have injected in the mold, you cool it down. Of course, if you cool it down in very quickly, so basically you go at a very low temperature, like 15 degrees, it's like you left your mold in open air, so it is at 15 or 20 degrees, so you cool down from more than 120, which is the melting temperature, which might be a melting temperature of some polypropylene. There are polypropylene which go beyond that, but in many cases it depends on the tacticity, on the disposition. In this case, we have a syntactic polypropylene, which, well, this is, of course, is not polypropylene. You can see the benzene rings, but this gives you an idea of how what tacticity means. In practical terms, the isotactic one, the isotactic polypropylene is able to go much further. But the syntactic polypropylene goes to 120 or so. And so if you cool down from 120 to more than 120 to 15 degrees, what you get a very different thermal properties across your polymer, and in practical terms you have also variability of mechanical properties and the possible insurgence of cracks. How we determine the glass transition by normally by a differential scanning calorimetry. So basically, you what is observable is that there are some differential dilatation, because what you see is that in rubbery state it is more with the same amount of heat you get more dilatation instead in a rubbery state. Instead, in glassy state you get less dilatation with the same amount. Easy. Or you can measure that by hand. In any case, you have some enthalpic peaks, which represent an amount of energy which is consumed to produce this transformation, which might be either endothermic or exothermic. In some cases, you might have also some effects of crystallization, which occurs also in PET. It's very cold crystallization is very important. So it's a very important phenomenon which you need to control, because if you have an uncontrolled amount of cold crystallization, you are not able to control the mechanical performance of the polymer. So you have the gas transition interval. Basically, as you can see also here, you can have, here we have the polyvinyl acetate, as I was saying, which has a gas transition between, in this case, 14 to 19 degrees, which means that it's very difficult to be used as such. So in practical terms, if the weather is cold, it is glass. If the weather is warm, it is rubber. You cannot use a material like that. You can use it in a blend, because of course if you introduce 20 or 30%, say, of this material into another polymer, in a blend of polymers, the glass transition temperature will change drastically, because of course will be obtained by the weight sum of the glass transition temperature. So you may remember that in polymers we measure Young's modulus, the elastic modulus, by um, complex numbers. So basically we have the E first and E second. E first is the real part, which we call the storage modulus, so the energy which is stored in the material elastically. And the E second is the loss modulus, which corresponds to damping and which corresponds in practical terms to the loss, which means that it deforms more than it should if it was elastic. And we define the ratio between the E2 and the E1 as tan delta, which is widely used in the whole of engineering in reality, because it's used also in electrotechnics to explain the lost energy over the actual energy. So basically, the losses also in electrotechnics are explained as tan delta. Tan delta has a peak at some point. For example, here we are talking about a type of polyethylene, which has got a peak of tan delta at around 140. Well, as always, it's not important. The values are not important because they are going to change for any polymer, but it is important the fact that with no, here we don't have any glass transition around. We may suppose it is already rubbery, so the glass transition temperature is below 20 degrees, we don't see it. But what we see is that the tan delta goes up, and we need to understand what is our problem. We need to understand up to which temperature we are able to use this material, which is going to be possibly 100 degrees, because somewhere, or even 80 degrees, because after that the losses become too high, which in practical terms means that the deformation of the material is no longer controllable. And therefore it's very unlikely to be able to use that material, which will deform also in a non-uniform way across the piece which you are using structure, which might be a sheet, which might be film or whatever. Okay, so in practical terms, this says one thing which is very simple, but it's good to know. Even if we have a low melting temperature, which is say 100 degrees, it is by no means true that we can use the material up to 100 degrees. We usually can use the material until the losses don't come too high. In this case, we can easily suppose that you see when we have the losses of the E1 and at 180 or even 200 degrees, we might have the softening. But in practical terms, we can use the material up to 80 degrees because after that, the losses start becoming higher. In some cases, it's not possible to measure the glass transition temperature and the other transitions, so the softening temperature, the cold crystallization with DSC, the differential scanning calorimetry. In these cases, we need to use the dynamical mechanical analysis. Dynamical mechanical analysis, basically you have an engine, a disk which applies the stress, a disk, whatever, whatever shape that applies the stress, and you measure the system by a system which measures strain. And basically, in this way, you are able to get, as always, a measurement of storage modulus, loss modulus, etc. This can be coupled also with dialectic analysis. Dialectic analysis is useful to see, in particular, the gelation time. The gelation time is useful in thermosetting matrices. In thermosetting matrix is a polymer to which you add something else. Where you add a hardener or a catalyst which is able to provide you with a cross-linking and basically to make a structure which cannot be molten, but on the other side it is very strong and much stiffer than the thermoplastic polymers. But you need to control that gelation time, and you know that by dialectic analysis, and basically you can see that you undergo a structural modification and so a variation of the electrical properties by the dialectic analysis. So sorry, I think you can see that you have a gas transition temperature. Load version of it. But anyway, I'll modify it when I put the file on my page. Anyway, the glass transition temperature, you can measure it by dynamical mechanical analysis. So basically, a glass transition temperature, you can also also the glass transition temperature increases the losses, of course. The rubbery, so what we are saying is that you have a rubbery Young's modulus and a so we have no version like anyway. I'm loading the other version. Sorry, but we get a 5 minute pause, and I load the right version. Okay, we resume what we were saying, and with this determination of TG by dynamical mechanical analysis. So basically, in this case, we may have we have a TG, um, we have a high crystallinity for polyethylene, and basically we need to determine the TG in this case, and you in reality you have an interval of values, and basically you have the number of possible measurements, so different possible values for this TG. Um, and this is not polyethylene. Of course, it's not polyethylene, it's a polystyrene. Um, polystyrene, because polyethylene would have a very low. And basically, you have this polystyrene, this high crystalline polystyrene, and you have the termination of the TG at high temperatures. And you have the different possible values which are obtained by the fact that the losses start to increase. So you have the onset of the tan delta, and then you have a peak of the tan delta and the onset of the decrease of the E1 and E2, etc. So you have different values. Apart from the figure, what it's important to remember is that there are some mismatches also between the values. You may have different values from which you can understand which is the maximum surface temperature after which it becomes rubber in this case. In the other case, this might refer to the TG might refer also to the melting temperature. You have the same problem. You have the same problem, and anyway, it determines the maximum surface temperature. Of course, once you have the complex modulus, you might have also the complex viscosity. Complex viscosity means that viscosity needs to take into account also the losses, and also that viscosity decreases with temperature, but decreases also with frequency. So in practical terms, when you say that the material is viscoelastic, in practical terms, it is practical terms, it depends on over time. Its behavior depends over time. If it depends over time, it depends also on the frequency. Depends also on the frequency, because the frequency, of course, it's an expression of time. This introduces an aspect which is important, the aspect of fatigue in polymers. Fatigue, therefore, cyclic loading. And you can have breakage at very low load if the frequency is very high, because it is true that you can have this is the shear modulus, and in practical terms, the shear you have here a G. The viscosity here is represented in that figure with eta. In reality, we well, it is possible also to use eta in some literature. They use also theta, but we usually use mu, and to represent the viscosity. And therefore, you know that viscosity is connected by the shear stress. So basically, you apply this shear stress and you allow the fluid to flow, depending on that coefficient, which is basically viscosity, which relates the shear stress you give and the flow you get. It is different here, interesting here that you can see some effect of cracks or presence or absence of cracks into this material. And basically, well, this is polyethylene, and basically you can see that there is a variation in shear modulus and therefore also in viscosity depending on the presence of cracks. So damage can have an influence also on the ability of the material to potentially flow. It is interesting also that tan delta has no influence on the frequency, but the losses can have a difference, can be influenced by frequency. Therefore, what I mean is that the losses, the mechanical losses, can be influenced by the number of cycles, the frequency of loading, in case the material is polar. Well, we were saying at the beginning of the lecture that non-polar polymers were the ones based on hydrocarbons, so which didn't have any other atoms than C or H. And so basically non-polar molecules, and therefore the consequence is that the structure tends to be a linear chain. A linear chain because you don't have any kind of hydrogen bond or polarities between the different parts of the polymer. In other cases, the material tends to be more convoluted, more closer on itself than linear. And for example, this is already the case with PVC, and you can have a kind of formation of pleated sheets, which is the normal situation in biopolymers like natural polymers like protein or cellulose. The two main main categories of biopolymers are proteins and polysaccharides, so derivatives of amino acids and derivatives of sugar. And in this case, they are strongly polar, and basically they depend a lot on the losses. The mechanical losses depend a lot on the frequency of the as the consequence, you can see that the deformation, the final deformation, depends a lot on the frequency of the loading cycles, which is not the case if the material is non-polar. Of course, you can also try to stabilize the material, because in practical terms, you can, of course, in this case, we have an epoxy. So basically, we don't have glass transition temperature because it's a thermoset. So it's cross-linked, and it doesn't undergo any changes between the glassy structure and the rubbery structure. It deforms very little, so it's closer to the glassy structure than the rubbery, but it's much stiffer. You can get to a few gigapascal. To have an order of magnitude, here we have a few gigapascal of Young's modulus, which is already good for, very good for polymers, this kind of polymers. So epoxy, it's one of the highest values we get in polymers. In resins, basically, because it's a thermosetting. And but it's very far from metal, from what you get with metal and what you get with glass. Anyway, it drops down at the moment you get to melting point, to the degradation more than melting, because they don't melt, they degrade. In fact, they drop down to zero, which wouldn't be the case in contrast with if it became a liquid, because a fluid, because fluid, you wouldn't drop at zero. Here you have a really degradation. And so what happens in practical terms is that you are able to push up this bio-epoxy. This is a bio-epoxy which is mixed with some styrene, and which acts as a plasticizer. And in practical terms, you can see that the more styrene you add, the more higher storage modulus you have, and the service temperature is also increased, because you have to stop at a certain point when you decide that your storage modulus it's below what you need for your application. So, for example, if you need 2.5 gigapascal, then you would need to stop somehow between 80 or 100 degrees, adding a considerable amount of styrene. So basically, you establish the service temperature also by the values of storage modulus, of as we were saying before. In fact, you can determine the service temperature by this measurements. So what is an elastovisco? In practical terms, you have an elastoviscoelastic material. And elastoviscoelastic means that you have a behavior which in some cases which is always the combination between an elastic behavior and a viscoelastic behavior. So in practical terms, a spring, which is elastic, and a dampener, which represent the viscous behavior. So practical terms, the deformation of a viscous liquid, which has the effect of time, where the effect of time is non-negligible. Practical terms, when you load and down and upload and download, or you have a loading and a deloading of the material, so you apply the load and then you remove it, what you find out is that yes, the hysteresis cycle. So in practical terms, you have some deformation left, which looks like plastic deformation, but you have also an effect of time. This is an animation of viscoelastic fluid, which looks like what's happening. In practical terms, you have a moment in which it appears not to flow, and you have it's not just viscous because there is a moment in which there is a correlation between stress and the strain, so elasticity. In practical terms, there are a number of models which can represent this. So the Maxwell, which puts together presence of the elastic and the viscous behavior, the Kelvin, which puts them into parallel, so series of parallel. Then you have the linear model, which assumes that the path is linear, plus you have a parallel between, part is elastic, so plus you have a parallel between elastic and viscous, and the Berger one, which assumes there is a series plus a parallel. But apart from all these distinctions, what is important to remember is that passing initially you have a linear relation between the strain and the time. So the strain is affected by the time, by the frequency, etc. In practical terms, the frequency is always has a direct relation with time. So there is a relation between the strain and time. The relation between the strain and the time can be linear. So if you increase by linear amount by some coefficient the strain of the time, you increase by the same coefficients also the strain. Then after a transition, you find out that the strain increases with increasing coefficients. So there is no longer linearity. This is interesting as well because we assume that there is a linearity up to a point, and this is important to know because up to this point we are able to process the material. If you want to mold the material, to inject the material into your molding system, you need to have this kind of linearity, otherwise it's going to be difficult to control it. This serves for production, but it serves also in service because after some frequency, the strain becomes exponential with respect to time, and therefore you are no longer able to control. In fact, you can see that with polymers, with plastic, we do only limited rotating devices because we have a limit into that. There are some more rotating devices you can see with glassy plastics. For example, first example you can see is the CDs which are made of polycarbonate. In fact, they don't suffer a kind of deformation in rotation. You wouldn't do a CD with a rubbery plastics like polyethylene because it might be the case that the deformation would grow with frequency in an uncontrollable ways, and therefore which leads to the breakage of the disk. Um, of course, we have creep as in metals. Creep not only at high temperature but also at room temperature. And basically, we have a number of possible measurements. Uh, as always, we have the three phases of the creep. We have the unsettled creep, we have the kind of constant, the kind of plateau of which is a kind of, it's not a real total, but you can say it is quite controllable, and then you have the propagation to tertiary creep. So creep is non-recoverable deformation with within elasticity or within the quasi-elastic state, yielding point, which is already difficult to establish for polymers, but anyway, you assume a um, quasi linearity between stress and strain, and despite this, you have some you have that applying a constant load, you might get a permanent deformation. And so you have the constant stress, and you have the so-called envelope. The creep envelope means one thing, that not for all stresses you get to the tertiary phase of creep. So the tertiary phase of creep is the one that brings you to fracture. So not for all stresses, thanks God, we have a creep fracture. We have an uncontrollable creep. Creep, as you may remember, is the deformation that occurs at constant load. So you do some tests, the so-called stress relaxation stress tests. So in practical terms, you apply a strain and you measure the stress which is necessary to keep the strain. At a certain point, you may get a fracture or not, depending on the situation of the envelope, depending on what is the stress necessary to keep this condition, and depending also, of course, on the stress. It is important that as the tensile Young's modulus has got an influence of time or of frequency, here there's this omega means frequency. Also, of course, the shear modulus, which is the one that allows you, for example, to extrude a piece. So the shear modulus is composed as well by a real part, so the elastic part, and the loss part, so the storage modulus and the loss modulus. Not much new here, apart from the fact that you have frequency as an effect, and as a consequence, you have fatigue also in polymers, and you can have fatigue also at very low loads. We don't have any kind of fatigue limit in polymers. You may remember the fatigue limit is the limit below that, below which you are not able to get to any fracture in any fatigue fracture. So in general terms, the life, as far as fatigue is concerned, the life of a component would be infinite. break for other reasons, but not for fatigue, not for cyclic load. In polymers, we don't have any fatigue limit, so any load would carry on a fatigue fracture. In other terms, there is always a number of cycles, however low the load that leads you to fracture, to breakage, to final fracture, or to collapse, as many like to say. And as always, also fatigue fracture has this structure in rings, which is typical of this phenomenon for metals and also for polymers. We are almost at the end, and I would like to say that here we have the three phases of this is the injection screw, and basically you have what is important is the clamping. Might be you have three situations. In practical terms, you have this sort of funnel from which you put your granules, your pellets, and they are pushed. They gradually soften and they are pushed towards the mold. They enter the mold. They are, which is clamped. And in the end, you have different kinds of clamping, hydraulic and mechanical. But what is important is to get the precise thickness. I have already shown you last time the possible defects. And it is interesting that when you start substituting the conventional plastics with the bioplastics like polylactic acid, you are always in search of the right temperature profile. So basically, you start from the pellets, as I've shown you before. Well, you have this funnel in which you put the pellets, then gradually you pass to the. They tend to soften, but gradually, and the screw is rotating. Meanwhile, it's rotating because they need to be effectively pushed towards the mold. Otherwise, they wouldn't flow. Of course, since all the things that you remembered here, the frequency of rotation it's important, because you would think that I can make them rotate at a very high frequency, but in the end, if you rotate them at a very get a lot of losses. So in practical terms, you get a lot of deformation, which practically results in you not be able to fill the mold because your plastic would go everywhere apart from the mold. So you would need to tailor your frequency of rotation in order with the requirement to fill the mold. And it depends on the type of piece you want to create. For example, here we have a process which is not exactly the same because it's a blow molding, and basically what you do, you blow instead of putting in the funnel these granules, you blow a preform blank, which is something that then needs to be finished. Gradually needs to be finished, but against the walls of your mold, you blow your plastic, which is already sort of softened. Also here you have a number of cases which involve different temperatures, and so in practical terms, you have an additional problem with polylactic acid pellets, because polylactic acid pellets, you can see here, drying of pellets, which means one important thing that, well, nice having bioplastics, but they absorb some moisture. And therefore you get to 80 degrees or so, 70, 80 degrees, depending on that temperature. So moisture is dissolved, and in practical terms, you are able then to melt them, to process above the melting range. You have here the melting range to be processed at a considerably higher temperature than the melting range. Then you cool down. Well, here what is not represented here are the times. Of course, cooling is not instantaneous, but then you have you cool them at the temperature at which you blow them. You are able to blow them in a sort of softened form. Then you dry them again, and you have to pass the glass transition. Again, this is important, that there is the limitation of polylactic acid, that we have a glass transition at 70 degrees. So we process them in the rubbery state, but we need to be careful at passing through the glass transition temperature and to cool down at the full temperature. And of course, the geometry is has a relation between the velocity of the process and the times involved. So I think that's all for today. Sorry for interruption. I know there's another file, but the file will be again in your page of the course, and we have two further lectures. Next one is going to be on Friday. We complete talking about the polymers. We are going to talk a little bit about biopolymers. And then we are going to have a last one, but the last one in which I will talk a little bit more about talking about biopolymers, past talking about biocomposites, so composites with the waste, or composites with like biomass or natural fibers. Let's see what we can do with the limited amount of hours we have. Of course, I think we have already done. Okay, so see you on Friday. Have a nice evening.